So welcome back to this last of the lecture series on this topic. And what I'm going to do today is that so far I've shown you some of the nanostructures that we make by surface patterning. And I'm going to talk about some of the sensing and biomedical applications using those patterns, and talk a little bit about opportunities and challenges in this area. So with that, let me show you most of our work application in sensors using these platforms we have actually published. Here's a list of the publication, and here's a list of the biomedical applications. So with that, let me move on to some of the sensing and biomedical applications that we'll talk about today. Chemical sensing on nanofibrillar TiO2 structure that we talked about that we create by hydrogen etching, core shell nanostructure that we create by oxidation of titanium alloys. And then I'll also talk about the fact that there is a real need for some systematic studies. And in that lecture, I'll tell you about some of the opportunities and challenges that lie in this topic. Then I'll move on to nanostructures for biomedical application, cell attachment and growth type application, DNA separation, and the pattern transfer by replica molding onto soft substrate. So if you recall, we make sensor film on top of a sensing platform. The film looks like a particle-particle contact that gives you this mechanism of electron depletion layer, back-to-back Schottky barrier created at the interparticle layer. And then this type of sensor is typically fully recoverable. You get introduce CO, resistance goes down, and when you cut off CO, resistance comes back up again. So we actually make this kind of sensor using the nanofibrillar structure in TiO2 that we talked about before. Remember that kind of etched surface nanofibrillar structure that we created. So we take this platform, attach two leads by putting gold paste and connect gold wire to the paste and cure it. And then that's basically your sensor. And we measured that sensor inside a furnace where we can control the gas concentration by diluting hydrogen. And we can do the measurement as a function of temperature as well. So with that, then you have seen that this is really the type of facilities that we have. Sensor will be inserted inside this quartz tube in the furnace, and a gas flow will be controlled by mass flow control system, and the sensor signal is acquired by the data acquisition system that is connected to a computer. So here's the hydrogen sensing. So we create this in hydrogen at 700, and now we're doing sensing of hydrogen gas at 400 degrees C. You can see that in the background, you get a steady signal, introduce hydrogen, 1%, resistance goes down, 2%, 3%, 4%. Cut off hydrogen, the signal comes back to the original level. If we take the 90% response values from this dynamic curve, we can plot this normalized response. This is not really sensitivity, but response as a function of hydrogen concentration. You can measure this normalized resistance, and you can figure out from this calibration what the hydrogen concentration is. It looks like this type of structure is working more or less as a very good hydrogen sensing device. Here are some of the ideas that I talked about exploring before in my earlier lecture. Remember that you can create TiO2 nanofiber by oxidation under deprived oxygen supply. So for the idea is that first you spread titanium alloy particles on the sensing platform, alumina substrate with interdigitated gold electrode printed on it, and do the argon treatment where you grow this TiO2 nanofiber, and then basically do the sensing on this kind of nanostructured platform. In collaboration with a Korean group, we have actually demonstrated the sort of feasibility of this kind of sensing idea in tin dioxide material. We'll publish this in here. So here is some idea that we talked about, creating p-n junction by putting different alloying elements on neighboring titanium particles, p-type elements or n-type alloying elements in the neighboring particles. That way we can get a p-n junction created by this nanofiber of TiO2 creating that junction. The junction would be at a length scale of tens of nanometer. And the other idea that we talked about before is that the barium titanate that we create by converting one-dimensional TiO2 in a hydrothermal environment to barium titanate, this dendritic morphology, this kind of structure can be used for selective detection of polar molecules like ammonia and SO2 and hydrogen sulfide and acetone compared to non-polar molecules. Here is an example of sensing using core shell nanostructure that we create in Ti64 alloy. Remember, we oxidize Ti64. We get this kind of core shell nanostructure where core is the TiO2 and shell is alumina. And this work was done with Professor Hasib's group in University of Malaya. And so here is some data from the paper his group published. They're looking at the resistance response as a function of time for different levels of hydrogen sulfide, methanol, and ethanol. And you can see that compared to hydrogen sulfide, methanol, ethanol sensitivity is better. And we can see that for different levels of these gases, you get different degree of response. So it works as a pretty good sensing device. It's not quite selective, but nonetheless, it's fairly sensitive to particularly methanol and ethanol. So one question that always comes up is that we create a core shell nanostructure. How does TiO2 picks up the response from the gas? Because there is a barrier layer. And what we believe is, since this layer is very thin, of the order of nanometer to tenths of nanometer, that the electron tunneling, and so electron tunneling assisted surface depletion layer on the TiO2. So the gas is interacting with TiO2 by tunneling through this layer in a way. The electron tunneling, the electron involved in the sensing behavior, creation of depletion layer, is created by tunneling of electron to that through that thin layer of aluminum. So I'm going to show you some data on the fact that this nanoheterostructure is becoming very, very popular in terms of gas sensing. In fact, the publications over the last 5 years, including 2023, and you can see that the number of publications is gradually going up each year. So there's a lot of activity, but what we found is that clearly there are a lot of opportunities optimizing heterostructure morphology and their spatial distribution, observing how crystallographic facets direct surface reaction. It's a lot of fundamental type of opportunities, and a lot of characterization and fundamental measurement type opportunities, as well as collaborating with other communities for application like catalysis, LED, solar cells, and biomedical communities. So clearly, many opportunities exist. Opportunities always comes with challenges. So determining some processing and manufacturing challenges, determining robust synthesis methods for controlling low-dimensional building blocks to desired architecture. Then you have to worry about depositing electrodes that will provide consistent material coverage. And then a lot of fundamental measurements, including a lot of the characterizations. And one has to worry about the measurement accuracy, and then linking the defect in the material to electrical conduction and hence sensing behavior. It's a lot of challenges. But what we found out is that there is a clear need for systematic studies. These people are making random structures, and different labs are reporting different results. So some systematic fundamental studies needed. So I'm listing here some of the things that we need to do. We need to understand the behavior of single nanowire, single junction, electrical characteristic, characterize electronic properties of the hierarchical structure, develop methods by which nanoheterostructure can be designed in a bottom-up approach for a specific application. And we have to also understand the influence of defect on electrical conduction and the sensing behavior. So there is a need for a lot of state-of-the-art characterization. We also know that you can get interfacial mechanism that we talked about, that you create this back-to-back Schottky barrier at the interface of particles, and the modulation of that gives you sensing. And then if you can have a homojunction of an N-type interface, or you can have a heterojunction, N-P-type interface that has an inbuilt interfacial barrier on top of the Schottky barrier. So there are, you can see that there's a lot of basic understanding that needs to be explored with the interfacial mechanism, but also with, since we are these days making one-dimensional structures, we have to think about, this conduction channel type mechanism that happens in one-dimensional structure. You can see that that's the width of the conduction channel before the absorption of oxygen gas. Once you absorb oxygen on top of that nanofiber or nanowire, you create this electron depleted layer. So you basically shrink the width of the conduction channel. And then when you expose it to the gas phase, now you can see that you're opening up the channel. So this modulation of the width of the conduction channel will give you sensing characteristic here. In addition to the conduction channel, one has to deal with the fiber-fiber junction that is modulated by the junction barrier that form. Now, on top of this, you can have, you can decorate the surface of the nanofiber by a secondary oxide that will further modulate the depletion layer, and one has to really understand the synergistic effect of the secondary oxide particles. There's a lot of fundamental understanding and studies that need to be conducted. And one of the students actually published a recent article summarizing how to organize some of these features into optimizing your sensing performance. So let's say if we are making a sensor using nanofibers or nanowires, we can align them on electrical contact pad in this fashion, and the current will basically flowing through the conduction channel. Or we can organize them perpendicular to the direction of the current flow on the two conduction pad. And in this case, the junction barrier height of the nanofiber junction will play an important role. So, which is preferable for sensing? Some people would argue this is preferable as opposed to the other one, because this will give you a high resistance, so you will get a larger drop in resistance, increasing your sensor response. Following along the direction of systematic studies, one can start with this lithographically refined platform made out of copper or gold or platinum with the contact pads there. And then you will spread your nanostructures on top of that platform, something like this. So you collect all this nanofiber, make a suspension, put a few droplets of the suspension onto this platform, and then dry it out and fire it. And then you have this nanostructures distributed on this platform. You can see that you can go into microscope and fib platinum, create a fibbed platinum contact onto one of this nanofiber, same on this side, and then you can fib out, cut out by fibbing again, cut out this part. Now you can see that you will have contact pad here, single nanowire contact pad there. You have created a single nanowire device. And in fact, here is a SEM picture of tin dioxide nanowire with two contacts contacting to the contact pads by fibbed platinum. So this is, not the most desired sensor device, but this is good for fundamental studies that you need to understand the behavior of a single nanowire. We can then build up 2 nanowire, 3 nanowire, and then we can capture, for example, single junction by connecting this one and that one to the contact pad by a similar process, and just keep studying the behavior of this single nanowire, single junction behavior, and based on that, then build up your, real sensor device. And obviously this will have to be coupled with modeling ideas, because this would be exhaustive number of experiments that you have to do. The idea is that you do some fundamental experiments, understand the behavior, and think about simulating how to create multi-nanowire, multi-junction sensor in an optimal way. So that's what is needed in this area. And then we also recently developed a open access database of resistive type gas sensors, where we input data into this database from published literature. And, so take application, We look at various sensors that the publication talks about. We categorize in terms of base material. Is it based on tin dioxide or TiO2 or zinc oxide? What kind of heterostructure? What kind of electrode material? And then we look at the response of gas analyte as a function of temperature, effect of relative humidity, and so on. And we look at the sensitivity and response recovery. So here's some screenshot of the database. You can see it has both data, creating the data by inputting data from published literature. And it also has a data search function. So once this database is quite robust and rich, we can actually search for example, if I want to search for what is the best material for CO sensing. So based on the database, it would give you an answer. Or what would be the optimum nanoheterostructure that gives you the best CO or NO2 sensing. So based on how rich your database is, it will give you a very resourceful answer. So we actually published a paper describing how it works, and we actually showed some case studies there, and you can access the database at this address. And the idea is that we are going to collaborate with our friends around the world who will help us put their own data, put others' data into the database to make it rich more. With that, I'm going to move on to application of nanostructure in biomedical application. So some of the application I'll talk about is cell attachment and proliferation, biological cell, DNA separation. So if you look at titanium and Ti64 as biomaterials, it has a lot of advantages. You can see it's utilized in orthopedic and dental application, exhibits very good biocompatibility, excellent corrosion resistance, superior mechanical strength and non-toxicity, can be directly bonded to the adjacent bone surface without forming a fibrous tissue interface, and it's biologically inert. So putting inside the body is safe. Some of the disadvantages or limitations are that titanium and titanium alloys are not bioactive materials. So they are not bioactive when implanted. So the target is to modify the surface in the hope that that would improve the bioactivity of the material. So that's where we started, and we create 3 different samples. So one is obviously the Ti64 control sample. We just take as is. So we cut coupons of samples, metal bars, with diamond cutter from the commercial sample, and then we mechanically polish the surface using 1200 grit silicon carbide sandpaper. After polishing, we go through some cleaning steps to make sure that there is no contaminants and so on. So that's your control cell. The other sample we use is Ti64 coated with titanium dioxide. And we make this coating deposit on top of that substrate by thermal spray coating type scenario. So, that's the coating process. And the other sample that we use is Ti64 that has this nanoware that was created by this oxidation process that I described. One-dimensional nanoware on top of the Ti64. So these are the 3 samples we used for biological tests. The surface cytocompatibility was evaluated by seeding human osteosarcoma cells, HOS, on autoclaved specimen at a density of so many cells per centimeter square. Okay, and then the cells were cultured for different amounts of times, and the medium, culturing medium, was changed every 2 days. So in terms of cell adhesion and proliferation, was characterized by fluorescence microscopy and laser scanning cytometry. And cell spreading and morphology were studied by SEM. And I'm going to show you some data. So this is 15-hour sample, 15-hour cultured sample. So this is the control sample. This is the oxygen TiO2 coated sample, and this is the sample with nanofibers. There's some variation, but it's very difficult to discern based on the fluorescence microscopy data. Now, these are the SEM pictures of 15-hour sample and 35 days sample. And you can see that this is the control. So we see this HOS cell on top of the surface. And then this is the oxide sample with oxide coating. We still see that HOS cell on top. And then on the nanofiber type sample, you can see that in this sample, you see some extracellular matrix and fibrils being generated. If you look at the 35-day cultured sample, the control doesn't show much of activities. The one with the TiO2 coating shows some, but not much. But the sample with the nanofiber now shows quite a bit of extension of this ECM and a lot of activities on the surface. So if you look at if you do cell count on these surfaces, so that's the control sample with TiO2 coating, don't see significant difference within the error bar, but the one with nanoware, you can see substantial difference. So clearly, the cell adhesion is increasing, is enhanced on the surface with nanofibers. And this is consistent with what people have seen in literature, that the nanostructure titanium-based surface upregulate the expression of specific bone proteins, such as OPM and BSP and so on. And BSP and OPM are known to contain adhesion-promoting peptide sequences. It's no wonder that this is being generated more on this surface, and that's giving you better adherence to that surface by the cell. Here is another study where we tested the chondrocyte joint cell test on the TiO2 nanoware surfaces. The density, culturing density was 15 times 10 to the 4 cells per square centimeter. And here are the SEM pictures of 1-day cultured sample, 4-day, 7 days, and 14 days. And these are different magnification of the SEM observation. So to summarize, day 1, we see this rounded and spherical morphology that resembles the typical chondrocyte cells. And 4-day culture, we see extracellular matrix fibrils expanding from cells. In 7 days, we see cell-to-cell contact via ECM. And then 35 days, 14 days, we see ECM extending and covering the entire surface. So the degree of this extracellular matrix interaction on the surface is gradually increasing. And again, with time, if you look at the adhesion and proliferation type measurements, you can see that it's gradually increasing with time. And this upregulation of cell numbers over time suggests that the chondrocytes have an affinity to the surface, to that substrate surface with nanofibers. So with the nano island that I showed you on the surface of YSZ, so those nano islands, if you recall, so here is an idealized view of that. So there is clear nano channels in between nano islands, nano channels. So the idea is that if you want to uncoil DNA or sort out longer DNA versus shorter DNAs, you can force the DNA through this channel and get this done. And the channel width is really in the right dimension, hundreds of nanometer, right dimension for DNA uncoiling and so on. So the idea is that if you force DNA from one end to the other while moving through this channel, nano channel, the DNA would have to be uncoiled. That's the whole idea. So did it work? And we track the DNA by fluorescence microscopy. So in this case, we're actually forcing DNA from the left to the right. And this was done under pressure gradient. We sort of mechanically force DNA to move from one side to the other. And what we found out, the DNA actually, all this bright color shows the extent of DNA that spread through the nanochannel, and you can see that it sort of traversed quite a bit of length, but then during the experiment, we had to put a roof on top of the surface. Remember, you have this hundreds of nanometer, it's actually 50 nanometer depth type channel. You have to put a roof so that you can force your DNA through those channels with a roof on top. But then after some time, the roof actually yielded. So DNA started coming out of the roof because the roof collapsed. So the idea that we got here is that the roof we put has to be an adherent type roof so that DNA can be constrained underneath the roof. And we also talked about this in our lecture, is that if these materials are not interesting, then we can use this as a mold and transfer this nano features onto a soft material like PDMS, simply by replica molding, where you cast your polymer on top of this and then cure the polymer and then peel off the polymer, and you can see that the patterns were very well transferred onto this polymer. And we have shown that we can do this with nano island and nano bars as well that we create on 110 oriented YSZ. This nano bars are magnification, and then by replica molding, we can transfer this onto and PDMS, and you can see the transfer is pretty good. So what, obviously, once you transfer, then you can do your biological cell attachment, proliferation, whatever else you want to study on this platform. The other important research that you can do in polymer science, polymer is typically sort of a spaghetti. So when you get this type of structure in polymer, you're aligning that spaghetti along those nanobar direction. So you can now study the anisotropic property of your polymer, viscoelastic properties, mechanical behavior. Now that the spaghetti is aligned and ordered, it's going to have an impact on mechanical property as well as electronic properties, like if you are doing this using electronic polymers. So with that, I'm sort of ready to conclude here. So there are a lot of challenges and opportunities, mass scale synthesis and fabrication. So this is typical materials R&D and materials manufacturing related topics. Assembling into devices and structures, nano packaging, bonding, adhesion, stability in hostile environments, a lot of surface and interface chemistry and physics type of study that is needed, fundamental understanding of properties relating to mechanisms and modeling type studies, and a lot of potential application, obviously sensing, catalysis, biomedical. I showed you some sensing application and biomedical application. Obviously people are talking about nanoelectronics, nanocomposites, photovoltaics, and corrosion related applications. But the field is robust with potential applications in different disciplines. And I'm going to conclude with the slide that I showed you before, whether this is all hype or is this real. Obviously, all this hyped type scenario came from mass media, but as I said, that as scientists and technologists, we have to rise above the hype and be realistic and have patience. So for some application, it's real only. And I mentioned only a few: analysis, sensing, biomedical, cosmetics, clothing, where they want to embed molecules to strengthen or induce other interesting chemical or physical properties. iPod Nano, for example, it already uses nanometer scale giant magnetoresistance memory cells. So for many systems, it's real. And for other systems like nanomotors, nanoelectronics, we need to have patience and continue to develop science, scientific understanding, as well as fine-tune the technology to get there. So I hope you have learned something from these lectures. And with that, I'm going to conclude here. Again, thank you for attending these lectures. If you have any questions, you can ask me now, or you can email me, and I'll be glad to answer your questions.